Assalamu alaikum warahmatullah and good morning. Today we are going to discuss the operation amplifier, which is open loop gain. So, dito sa open loop gain, dun sa lecture na sinend ko dun sa materials pala na nababasa niyo sa Google Classroom, the open loop gain usually referred to the gain, okay? Gain voltage. Ito yung gain voltage na yung open loop gain, right? And the gain of the amplifier without the feedback loop being closed, hence the name open loop. Okay, so kaya tinawag yan open loop kasi nga it's not actually referred. It's obviously or common sense na it's not being closed, right? So for appreciation of operational amplifier, this gain can be very high on the order of 160 decibels, okay, or more. This is a gain of 100 million. So this gain is flat from DC to what is referred to the dominant pole. So from there, it falls of the gain. Okay, so dito yan. Ito yung mga graphs makikita natin. So ito yung open loop gain. So it's flat. Nag-flat siya dito. So this gain is flat from DC to what is referred 2 as the dominant, okay, as a dominant, as a dominant pole, okay, as a dominant pole, right? Yan. So from there, it falls off at 6 dB. Ito yan. Nag-falls siya. So meron tayong 0, okay, 1, 2, 3, 4, 5, okay, tayong 5, 6, 7. Okay, so dito naman 0, 1, 2, 3, 4, 5, 6, parang ganyan. Okay, so basically it falls pagdating dito sa uh, bawa yan. So 1, tapos 2, 3, 4, okay, 5, tapos yan. Okay, so dito naman is 1, 2, 3, 4, 5, 6. So, bawa dito yan sa 6. Paano naman ito? 1, 2, 3, 4, 5, 6. So, dito sa 6. Yan, from 6. Okay, itong 6 na yan. Nag-drop. Okay, nag-drop siya. From there, it falls off 6 octave or 20 decibel over decade. Okay? An octave is doubling or doubling in frequency. And okay, and decade is 6 is times 10 in frequency. This is referred to as a single pole response. It will continue to fall at the open loop at this rate until it hits another pole. So in the response, this second pole, ito yung second pole, okay, second pole will double the rate at which has dropped below 0 dB. So nag-drop siya pa 0 dB hanggang 0 dB in gain before it hits the second pole. So the operational amplifier will be ito 0 kasi yan. 0 yan. Okay. Operational amplifier has dropped below 0 dB unit gain. So before it hits the second pole, the OP amplifier will be unconditionally stable at any gain. This will be typically referred to as a unity gain stable on the data sheet. If the second pole is reached while the loop gain is greater than 0, greater than 1, 0 decibel, then the amplifier may not be stable under some condition. So bakit hindi siya mag-stable? It is because yung yung ah, yung dB niya is continuing yung na patuloy siya nagda-drop. So patuloy yung pagda-drop ng ah, gain. So pababa hanggang sa maging zero siya. Okay? So yung tinatawag natin na open loop gain. In this lecture, we are going to discuss the open loop gain under the operation amplifier. So I attach a video, I embed a video presentation from the YouTube regarding to the operational amplifier on the open loop. So it's titled Open Finite or Operational Amplifier Finite Open Loop Gain. So let's watch the video. This video contains ads, so we just need to wait until the video presentation will to shown in the video attached on this lecture.
Hello everyone, welcome to episode 13 in the Op-Amp tutorial series, Op-Amp Finite Open Loop Gain. Today we're going to introduce the concept of traditional feedback analysis, rather than the simplified version we've been doing with the ideal Op-Amp tenets. Then we'll explore the effect of finite gain on the non-inverting amplifier's gain, and use those conclusions to look at the effect on the inverting amplifier's gain. Ending with the specific effect that finite gain has on the input resistance of the inverting amplifier. As an additional note, we will be assuming infinite bandwidth for this video, since that's the best way to introduce this topic, though we'll discuss finite bandwidth soon enough. The op-amp non-ideality we're discussing today is a big one, finite gain. So the value of AV is no longer infinity, it is a finite value. This breaks our central op-amp equation to the point where we can't really patch it up like we did with the input offset voltage and input bias current non-idealities. So instead we'll need to discuss how to do feedback.
For the link of this video, I will upload this one on the link. I mean on the Google Classroom, so you can copy and watch some other tutorial and related to the operational amplifier. Okay, let's continue.
Back with an arbitrary amplifier rather than an ideal infinite gain one. Again, we're going to assume infinite bandwidth, so gain and or transfer functions are each just represented by a single number, not one that changes over frequency. This will simplify things significantly to start with. So let's look at a block diagram of a feedback system. So here we have three main components: the error amplifier with gain AVOL, which means open loop gain, which is the gain without feedback when the feedback loop is open, the feedback network with transfer function beta, and the summing node which subtracts the FB signal from the input signal. Note again that AVOL and beta are both just single numbers in this infinite bandwidth setup. There is no frequency dependency because we're not considering frequency here. It's worth noting that sometimes there are circuits that are not really the error amplifier, that are placed between the error amplifier's output and the feedback connection node that gets fed to the beta block. An example of this is the integrator subcircuit made with a second op-amp that we used in the previous video as part of the input bias current measurement circuit, which wasn't part of the first op-amp at the front end, but also wasn't part of the feedback loop. For simplicity, we'll just combine the error amplifier block and those additional blocks together into one block and call it the error amplifier. This is usually acceptable unless we're trying to analyze one of those secondary blocks or examining the signals between those blocks. For today, though, we'll just treat all those blocks as one aggregate block. There are a few things we should note about this feedback system. This feedback system implements negative feedback. This means that the signal fed back from the output, labeled here as FB, is subtracted from the input signal. This also means that AVOL and beta must always be the same sign, usually both positive. A negative feedback system always produces a closed-loop gain magnitude lower than the gain magnitude of the error amplifier. And finally, positive feedback is undesirable, as it causes an amplifier to become unstable and have infinite gain, thus causing the output to rail or oscillate. We'll discuss instability in more detail in a later video. Signals, which could be currents, voltages, or other kinds of signals like digital signals or power signals. Today, to make it a little easier to visualize, we can make all the signals voltages. So now we have our 4 voltages labeled. Let's do some calculating. We can't calculate Vout directly yet, but we can calculate other voltages in terms of Vout. So we have VFB equal to beta times Vout, and we have the error signal, Verr, equal to Vin minus beta Vout. Now we can calculate Vout equal to AVOL times Verr. Now with substitution, we see this is equal to AVOL times Vn minus beta Vout. So now we distribute and consolidate all the Vout terms on one side to finally get a value for Vout. And we just divide both sides by Vin to get the transfer function for the closed loop gain of this feedback system, denoted by AVCL. Again, while I've put voltages here, it can work with currents or other kinds of signals, including digital or differential signals. So the first thing we're going to do here is see...
Alright guys, this is how to solve the voltage out using the voltage gain, okay, gain voltage. So we can actually use this formula to solve the voltage out in an open loop gain operational amplifier.
See what happens when AVOL approaches infinity. When AVOL times beta is much greater than 1, then 1 plus AVOL times beta is approximately equal to AVOL times beta. And thus, the open loop gains in the numerator and denominator of the closed loop gain equation cancel out, and the closed loop gain is approximately equal to 1 over beta. So if there's enough gain in the error amplifier, we can control our approximate closed loop gain just by controlling beta, and fluctuations in the error amplifier gain don't affect the output much so long as the gain remains high. Since we generally want a closed loop gain of 1 or more, that means beta will be 1 or less, and so we can easily set the value of beta using only passive components like resistors and capacitors. Resistors and capacitors are much easier to make with precise characteristics than the gain of the error amplifier, so we're effectively using large open loop gain and negative feedback to make the system more precise, just as with the ideal op-amp equations. So we see that the quantity AVOL times beta is a central parameter of the feedback system. This quantity is called the loop gain. The loop gain is not the closed loop gain or the open loop gain. It's a third quantity, perhaps not very well named, but it is the name that is generally used. The loop gain is a measure of how much gain the feedback system can use to enforce the infinite gain approximation of the system. The higher the loop gain, the closer to the ideal it can be. Notice that beta directly attenuates the loop gain when beta is less than 1, and beta is almost always less than 1 for passive feedback loops. This means the smaller beta is, the smaller the loop gain is. This makes intuitive sense because...
Okay guys, no, take note that the lower the feedback gain, the lower the beta is, alright? So, yun yung pakitandaan yung slogan na yun, or yung quotation dun sa, yung quote dun sa binanggit niya kanina sa video, right?
Because when beta is smaller, then the overall closed loop gain of the circuit is larger, so there's less gain left over in the error amplifier to push the closed loop gain close to the ideal. The loop gain is even more important later when we talk about the frequency effects and stability of op-amp feedback loops, because the conditions when loop gain magnitude gets very close to unity are very important for stability. So now that we've discussed the traditional negative feedback system, let's apply to the non-inverting amplifier. So here we have the standard non-inverting amplifier, and the equation for the closed loop gain we just derived. Taking a closer look at this circuit, we can think of the non-inverting amplifier as a circuit that takes the output voltage, puts it through a resistive divider, then takes the output of the resistive divider and feeds it back to the input side. So, the input and output signals are voltage. The feedback network is measuring the output voltage, then dividing it down to produce the feedback voltage, VFB, which goes into the inverting amplifier input of the op-amp, which serves as both the summing node and the error amplifier, with the error voltage Verr represented by the difference between Vin and VFB. So that's the conceptual breakdown of the non-inverting amplifier. By inspection, we see that the value of beta is simply the resistive divider equation, since that's the transfer function that is applied to Vout to produce VFB. So, substituting this value for beta into the equation above, we get this expression for the closed loop gain. Now with this equation, we should be able to see why the infinite gain approximation works well. So first, let's multiply the numerator and denominator by 1 over AVOL, and we get this equation, which in the denominator has 1 over AVOL plus R2 over R1 plus R2. So we see that if the loop gain is very large in magnitude, then 1 over AVOL becomes much smaller than R2 over R1 plus R2. And so we can approximate 1 over AVOL to be approximately 0. And then the equation becomes 1 over the resistive divider equation, which of course is our ideal non-inverting op-amp gain. So we can see how the equation becomes approximately the same as the ideal case when AVOL is large. Next, let's take a look at the gain error for different gain values and different beta values for the non-inverting amplifier configuration to give you an idea how much finite gain causes deviation from the ideal case. So here we see that with open loop gains that are not much higher than the ideal closed loop gain, we see significant errors because there's not enough loop gain to enforce the ideal result. And in order to get around 1% error, you need to have a loop gain of at least 100. We can see that the parameter that matters for percent error from the ideal is the loop gain, and the specific values of beta and AVOL do not matter. And the magnitude of the error is approximately equal to 1 over the loop gain. At very high loop gains, the errors become so small that the errors in the gain are swamped out by the errors in the gain setting resistors, and thus in those cases it is better to use the ideal op-amp gain equations rather than this more accurate version. This also displays a fundamental point and the original reason for the concept of negative feedback, that for high loop gains, the closed loop gain is very insensitive to open loop gain fluctuations. To illustrate this, let's just look at the case when the gain is 10,000 and beta is 1 over 10. So the loop gain is 1,000 and the closed loop gain is about 9.99001. Now let's increase the gain by a factor of 10 to 100,000 with the same beta. So the loop gain is 10,000 and the closed loop gain is 9.999. Calculating the percent increase in closed loop gain due to this tenfold increase in open loop gain, we see that even though the open loop gain of the op-amp has changed by an order of magnitude, the closed loop gain has changed by less than 0.1% in magnitude. This means that our op-amp doesn't need to have a reliable gain. It doesn't even have to be linear. So long as the minimum gain is large enough, things like temperature and nonlinearities can change the open loop gain a lot without causing any significant effect to our circuit. This was one of the main reasons negative feedback was invented. It can eliminate the errors and nonlinearities in the internal circuitry of the amplifier core and linearize the gain function using a feedback network of linear components, which usually consists of just resistors and capacitors. So now that we've applied the traditional feedback methodology to the non-inverting amplifier, let's move on to the inverting amplifier and see what differences there are when applying this traditional feedback methodology to it. In the inverting configuration, the non-inverting input is grounded, or connected to a static voltage, but once we have the grounded solution, we can use superposition to easily adjust for the non-grounded version. So we start by solving for the voltage at the inverting input, but without the ideal op-amp equations. It's a little less clear how the feedback is set up here with the inverting amplifier, so we'll start with Kirchhoff's laws. Keeping the other ideal op-amp assumptions of input offset voltage and no input bias currents, the input is simply a resistive divider between the input voltage and output voltage. So we separate out the terms containing V in and V out and simplify. Thinking about the general feedback structure, we recall that V error is equal to VOP plus minus VOP minus. So we can substitute in 0 volts for VOP plus and the expression above for VOP minus. After simplifying, we see that the coefficient on V out is the same beta as the non-inverting amplifier, with the appropriate sign given the summing node. The input side has a different coefficient and a negation. So the way we capture this is by putting a transfer function after the input voltage prior to the summing node, which includes the negation that is characteristic of the inverting amplifier configuration, and we're left with this feedback block diagram. Note that beta is the same, which makes sense, since the inverting and non-inverting amplifier circuits have the same structure when the input is zeroed out. So now that we have the feedback loop structure, let's finish the equation. So the final equation we need to solve for is V out equals AVOL times V error. So we plug in our expression for V error, consolidating terms and simplifying, we get the following closed loop gain. With some slight rearranging, we can see that it's the same equation as the non-inverting amplifier version, except with the negative R1 over R1 plus R2 block multiplied in the front. And with the infinite gain approximation, we get rid of the 1 in the denominator, which allows us to cancel out a few terms, leaving us with the familiar ideal gain value we derived using the ideal op-amp equations. So we see that the inverting amplifier has the same loop gain as the non-inverting amplifier, and the table we showed previously comparing the open loop gain in beta with the error is the same. The only difference is that the closed loop gain will be negative and 1 less in magnitude than the values in that table. One difference between the non-inverting and inverting amplifier is the input impedance. With the inverting amplifier, the input impedance we've computed thus far has hinged on the infinite gain approximation. So let's see how the input impedance changes when we apply finite gain. Note that we're still using the ideal op-amp tenet of zero input bias current. So the definition of impedance is the change in voltage divided by the resulting change in current. So what we need to do conceptually to calculate the impedance is to provide an input test voltage on Vin and calculate the resulting input current In. It may seem a little odd to conceptually inject voltage into a circuit diagram when it's not a real physical circuit, but it is usually the most effective method of calculating impedance for a linear circuit, even if it does feel a little like you're testing a non-existent circuit. So first we rearrange this equation to get an expression for Vout in terms of Vin. The easiest way to get a current for this circuit is to find an expression for VOP minus in terms of Vin and known constants, then take the difference between Vin and VOP minus and divide that by R2. Then once we have the current in terms of Vin and constants, we just calculate Vn over In, and we'll have an expression for the impedance Zn. Fortunately, we can start with this expression for VOP minus we derived earlier in the video, then substitute in our expression for Vout above to get an equation for VOP minus that is in terms of Vn and constants. So at this point we've done all the conceptual mathematical steps, and the remaining algebra for computing Zn after this is a bit tedious and doesn't require anything weird or fancy like partial fraction decomposition or anything like that. So I'll show the slides for all the steps for completeness, but won't go over each step. The equations in blue at the top of each slide are just a copy of the last equation from the previous slide. Pause the video if you would like to take a closer look at each step.
Alright, so that was all the okay, you can take a photo for this inverting amplifier input resistance. Pwede niyo po yung tingnan. Okay.
Hello everyone. Welcome to episode.
This is another type or ito yung mga style or types of the traditional amplifier. So meron tayong first is the inverting. Bakit natin tinawag yan inverting? It is because yung input ng voltage is directly to the uh, this is non-inverting rather, sorry, it is non-inverting kasi yung input niya is pumasok dito sa positive. At the same time, yung ito, hindi naman yan non-inverting. It is inverting. It is because yung positive is going to the ground, and on that input is directly to the positive as to the negative. So this is inverting. Ito rin inverting yan kasi pumasok yung input kuryente doon sa uh, negative sign. So it's directly going to the ground. So this two is inverting and the other one is non-inverting. Alright, so voltage, noise, and offset voltage on the top on the operational amplifier are reflected to the output by the noise gain. So it's also explained on the YouTube on the video presentation. So I will upload a video presentation related to the operational amplifier open loop gain. So noise gain, not signal gain, is relevant in assessing stability. And then circuit C has unchanged signal gain, but the the higher noise gain, those better stability, worse noise, and higher output offset voltage. Right? So yun, yung operation amplifier and a different stages. So meron tayong mga iba't ibang klaseng operation amplifier. Alright? That's all for our discussion and related to the operational amplifier open loop gain. So these are the stages. Meron pa iba't ibang iba't ibang klase na discuss natin. And hopefully you can analyze and also try to read a lot of um, books and related or articles related to the operational amplifier. Uh, Abangan nyo po yung quiz natin. The same thing. Dito rin sa, ito yung video presentation that we are going to use. Yung mga answer ay makukuha dito. So, basically, lahat ng mga answers ay nandito rin at hindi nyo kailangan pang hanapin sa iba because I will not include on the quiz kung wala siya dito sa video presentation. So, once again, good luck for your quiz and try to read a lot of books in related to the operational amplifier. So once again, Assalamualaikum warahmatullahi ta'ala wabarakatuh.